For this, we're just going to jump straight in with an example where we have set A is 1, 2, 5, 6, 7, 9, B is 1, 3, 4, 5, 6, 8, and C is 3, 5, 6, 7, 8, 10 under the universal set consisting of natural numbers less than 11. That is the numbers 1 to 10, where we want to find A union the quantity B intersect C, A union B intersect A union C, and A complement intersect the quantity B intersect C. So we have each of these three cases, and starting with that first one, what we'll want to do there is take care of what's inside of the parentheses first, like I said earlier. So we want to get B intersect C. And to get B intersect C, that means taking the intersection of B with C, 1, 3, 4, 5, 6, 8, and 3, 5, 6, 7, 8, 10, where we can see that the elements that are shared there would be 3, 5, 6, and 8, so that's our intersection. Meanwhile, we take that with the union, or take that in union with A, excuse me, I want to get my verbiage just right there. So we're taking the union of 1, 2, 5, 6, 7, 9 with 3, 5, 6, and 8 to get basically everything except for 10 and 4. 1, 2, 3, 5, 6, 7, 8, 9. So far, so good. It's the same sort of operations as before. Maybe it would help if you think about it as just taking those intersections of things as being one set into itself, because that's what it ends up being. It's just you've got more notation around it. And that means if we do the second case, we can start with each of our unions. So with our first one, we started with the parenthesis, or the intersection inside the parenthesis, excuse me, my wording's having some trouble. Here, we're going to start with the unions inside of the parentheses. So we're going to take A union B, which would end up being 1, 2, 3, 4, 5, 6, 7, 8, 9, along with A union C, which would end up being 1, 2, 3, 5, 6, 7, 8, 9, and 10. Based on the pieces that we have there in terms of what is shared across either. And then if we take the intersect of those two pieces, A union B intersected with A union C, we're going to be intersecting 1 through 9 with 1 through 10 without 4, which will leave us with 1, 2, 3, 5, 6, 7, 8, and 9, which if you're paying attention, you should notice is precisely the same as what we got from the original case, which hints at an important thing in terms of equalities between set operations, which we'll talk about later, but in particular a thing like the distributive law for dealing with set algebra. And that actually is true, but again, we'll talk a little bit more about that idea in a bit. For our last case, if we want to do this sort of thing, again, we want to deal with things like the complements and those parentheses first. I'm going to do the complement first because it's outside, and then we can do the intersection afterwards because, well, we've already done the intersection anyway. For A complement, we're taking everything other than A, which is going to end up being 3, 4, 5, 8, and 10. And then for B intersect C, we already have that. That's 3, 5, 6, and 8. So if we intersect those two sets, we can see that 4 is in A complement, but not the intersection, while 5 and 6 are in the intersection, but not A complement. I forgot about 10. That one's also just in A complement. So we're left with 3 and 8 in terms of the universal set from 1 to 10. Again, things with complements by necessity have to be defined by universal sets. Here we're going from 1 to 10. I could have made that bigger, could have changed that somehow, but that's what we have. Anyway, hopefully you're seeing here with these examples that the process is very much the same as what we did in the last section, except now we just got some more ideas to chase around, some more details we have to be careful with. It still works in the same way for the same reasons. So when we take these ideas and instead apply them to Venn diagrams, we're going to see that it still works in the same way, except our pictures are a little bit more complicated.